Okay, so let's start off by talking about, well, first, let's get a slide on recursion and talk about that and give the kind of little intro material for recursion. And then we're going to just jump right into an impossible recursion problem. So recursion is when a function or method calls itself from within itself. Now, generally speaking, I guess this is appropriate to what would have been reintroduced this now because recursion uses the stack, uses a stack data structure to temporarily store the state of a function as another call of the same function takes over. And let me give you an example of recursion. Actually, let me just add a couple more things here. Recursive solutions tend to be very short compared to iterative solutions. And we could actually put a little side note here saying that any problem that can be done recursively can be done with a loop and a stack. So we can accomplish recursiveness without ever using recursion by using a loop and a stack, but I think people typically would not do that. So recursive solutions tend to be very short compared to iterative solutions. Recursive solutions are very memory inefficient since we need to store all of the information about a running method when it gets put on hold while it waits for its clone to finish. All right, so some of that will make more sense once we see some examples. So let's start off with the simple recursive example. So that is the factorial problem. So many problems that you could do recursively, you could also do with a loop anyway. So not very often are you actually pushed into a situation where you have to do something recursively. But sometimes recursion does lend itself to a problem because, again, when we're solving problems with a programming language, we tend to, well, we're meant to try to solve them in a way that's very similar to the way we solve problems in real life. So if we think about factorial, and let's think about 4 factorial. So 4 factorial, well, that's 4 times 3 times 2 times 1. So that's 24. That's what 4 factorial is, right? All right, so, but 4 factorial is actually equal to 4 times 3 factorial. And 3 factorial is equal to 3 times 2 factorial. 2 factorial is equal to 2 times 1 factorial. 1 factorial is equal to 1. So if we're calculating 4 factorial, we can say, is this guy equal to 1? If not, return 4 times that guy minus 1 factorial. Call the function again. So that means this whole guy gets put on hold because it's waiting. So this guy waits for 3 factorial to finish. We ask the question, is this guy 1? Nope. So we're going to return 3 times that guy minus 1 factorial, 2 factorial. So this guy can't finish yet. So he also waits. So all this information was pushed onto the stack. All this information has now been pushed onto the stack. That means all the variables, all the parameters, everything you need to reconstruct that function have now been pushed onto the stack while it waits. 2 factorial, is this guy equal to 1? Nope. So we return 2 times 1 factorial. And this guy waits. Now we're waiting on this guy. 1 factorial. Is this guy equal to 1? Yes. So we return 1. We're done. So this is able to finish, which then allows this guy to finish, giving us a 2, which then allows this guy to finish, giving us a 6, which then allows this guy to finish, giving us a 24. See how that works? So we discover that the idea of 4 factorial, the idea of factorial is a number times the factorial of something 1 less than itself. And we only stop once we get to the stopping point where we no longer call the function again. So if we were to write that, I'll just quickly write it here. So we might have a function that returns an int, just allow there to be some uppercasing stuff here. This is a simple example, maybe called factorial. It takes an int n as a parameter. We ask the question, if n is equal to 1, return n. Otherwise, return n times factorial of n minus 1. So that's the factorial function, written recursively. So if n was 4, is 4 equal to 1? Nope. So we drop down to here, we return 4 times whatever factorial of 3 returns. So now this guy gets put on hold because we have to wait for this. This function blocks. So it loops back up. Is 3 equal to 1? Nope. Return 3 times factorial of 2. Loop back up. Is 2 equal to 1? Nope. Return 2 times the factorial of 1. Loop back up. Is 1 equal to 1? Yes. So we return 1, which then lets the previous guy finish, which then lets the previous guy finish, which then lets the previous guy finish. Finally, we have our answer. All right, so questions. Josh has a question. Go ahead.
So you said anything that can be done recursively can also be done with a loop and a stack. Can any problem that can be done with a loop and a stack? Is there any problem that can be done with a loop and a stack that can't be done recursively?
I guess my safe answer is maybe. My feeling is probably not. I don't know that it's important, I guess would be the starting point. Really, that statement of anything that can be done recursively can be done with a loop and a stack, that's more of the nature of people tend to be scared of recursion. It's kind of hard to wrap their mind around at first until you get good at it. Once all of you take the 470 class where we write a programming language, we use a language that doesn't support loops. So you have to do everything recursively. And you'll get pretty solid at it then. But you know, I guess that statement really has more to do with if you had to avoid recursion, if you were just gun-ho on avoiding recursion, you could, instead of using the way recursion works behind the scenes is it uses the stack to hold on to the temporary state. So it used the stack to hold on to the temporary state of this guy while it executed this guy. Then it used the stack again to hold on to the temporary state, kept pushing these guys onto the stack on top of each other until it finally hit an endpoint where it could unravel. So since recursion is implemented using the stack, you could choose not to use the built-in function, but instead to build your own loop and stack to emulate the idea of recursion. So the flip side then would be if you're trying to see, is some problem I didn't think about recursively that I used a loop and a stack for, could I implement that recursively? My gut feeling is probably. But again, I'm not sure it necessarily matters to like know that for a fact. All right. So as we go, if you have questions, just blurt them out, because I do see the group chat, but it's up above, so I might not be looking up at it since I don't see video faces right now. I might not see you waving your arms and stuff like that.
So is this faster or slower than a loop would be?
Say that again?
Would this be faster or slower than a loop? In, like, you know, theory, like,
I understand what you're saying. It would be slower than a loop because it takes time to kind of gather all this stuff up, push it onto the stack, and then call it again.
Okay.
So if you wanted to kind of connect like a weird dot, I'm not sure these are really connected, but it's maybe a way you can kind of think about it, is recursion is kind of like linked lists, where iteration is kind of like arrays. So arrays are fast. Well, actually, that's not even a fair statement because the recursion is memory inefficient. So yeah, that's not a fair assessment either.
All right, so it's like it saves the coder some time. It might not necessarily be the most efficient for the computer process.
Yeah, so maybe one way I'd put it is this. Let's just put another recursion facts. We'd say recursion is slower, memory inefficient, but usually we'd say something like relatively elegant. And by that, we typically say shorter solution, because a lot of the magic is held inside of the recursive call. So you get relatively slow code that's also memory inefficient, but it might look pretty slick, something along those lines. But then again, sometimes it's also the only way to solve a problem, or the most obvious way of solving a problem. You'd have to do a workaround. I don't know if I have a good example for you for that, but you'd have to find a workaround. I guess merge sort would be a good example of that. The problem we're going to solve today, I think, would be very, very difficult to solve iteratively. Recursively is how it makes sense.
That makes sense.
All right, so let's keep going. Let's start talking about merge sort then. So when we talk about sorting, so sorting means put stuff in order, right? So put stuff in order. Now we're going to start off with a fact about sorting. If I gave you the collection of numbers 2, 1, 3, and I ask you, is that sorted? All of you would say, no, that's not sorted, right? How do you know it's not sorted? This goes back to CSC300 about human beings are so good at solving problems that we have trouble articulating how we solve them. How do you know that that's not sorted?
The values aren't arranged greatest.
Okay. Now I'm going to keep, well, here, everybody's going to close their eyes. I'm going to write new numbers here. And then I'm going to hide the numbers from you. All right. Those numbers are black in color. I have 3 numbers here. Are they sorted? The real answer is we don't know, right? A human being, we'd have to see the numbers. All right, so now I'm going to say, I have 2 numbers. Are they sorted? Actually, I only have, put the second number back in. I have 2 numbers. Are those sorted? We'd still say, I don't know. I got to see what the numbers are. All right, now I have 1 number. Is that sorted?
Yes.
Yep. So a 1 list. A list with exactly one number in it, by definition, is sorted. All right, so that's a fact that merge sort relies on. So a list with one value in it is called trivially sorted. It only has one thing. It's sorted. It's already in order. All right. So if I gave you one element and I said sort these, you would just hand it back to me and you say, I'm done. I didn't have to do anything. I didn't even have to look at the value. It's sorted because there's only one of them. Okay. So that's a fact that merge sort operates off of. Not a incredibly amazing fact, but a fact nonetheless, and something that maybe we would not have necessarily said out loud otherwise. All right, so let's talk specifically now about merge sort. So merge sort, I'm actually just going to do this by an example. It's easier to show this as an example. Keep it short. We're only sorting 5 things. It should give us enough iteration to see this. All right, so we start off asking the question, is that sorted? The answer is no, because it's not a one list. A human being can look a little deeper and glance at it and say, yeah, those aren't in order. All right, but because this is not sorted, we ask the question, is this sorted? No, because it's not a one list. So what do? We're going to divide it in half. Now, how we divide it, so right now I have an odd number of things. It doesn't matter if I have the larger number of things to the left or the larger number of things to the right, as long as I'm consistent. If I always have the larger number to the left or larger number to the right. So we're not going to do any of the math for this yet. I'm just going to visually do this. So we're going to say this guy is not sorted. So what I'm going to do is I'm going to split my data in half.
I just have a quick question.
Go ahead.
Why are we, so I understand what merge sort does. I'm just confused as to why we don't just sort it. Why do we, what's the difference between just sorting a list and then splitting it a bunch of times and then sorting it? Like, what's the benefits of that?
Well, merge sort accomplishes its sort by splitting it over and over again. And it is very fast, especially when you split it over multiple cores of a processor or multiple machines.
So this is like faster than just sorting through a whole big list. It's better to just, it's faster to split them all and then sort them?
Well, okay, the splitting it is the sorting process. So the sorting process here is accomplished through splitting.
Okay.
So when we say sorting, you know, I can give you a deck of cards and tell you to sort these, and you know, there's a whole bunch of approaches you could take to sort a deck of cards, for example. So the one we've done before is an insertion sort, where we started at bucket 1. Remember, we had the follower and something kind of bubbles up towards the front, that kind of stuff. Well, this is an alternative to that uses recursion for sorting. There's the two kind of, this guy is tied with another guy called quicksort for the what are considered the fastest sorts out there. Merge sort really shines when you have multiple processors or multiple computers sorting the data, because you can hand parts of the problem off. You can divide the problem up very easily and have parts of your collection be sorted by different computers, and then them all come back together to ultimately give you the answer.
So when it splits, are we sorting them as they split, and that's why it's faster?
Why don't you hold the question until that particular question until we get to the end? It'll make sense.
Okay.
So yeah, because we haven't actually started sorting yet. All we've done is we've said, This guy is not sorted because it's not the one list. So we're going to split it in half. And now what we're going to do is we're going to call merge sort on this half, and we're going to call merge sort on this half. All right, so we have two calls to merge sort here. So we're calling merge sort on this half, and we're going to call merge sort on this half, keeping in mind that we originally called merge sort on this entire list. So we called merge sort on this entire list, and we decided this guy is not sorted because there's more than one thing here. So I'm going to divide it in half, and I'm going to send the first half back into merge sort, and I'll also send the second half back into merge sort. Now, one thing you're going to see here is we're never going to get to, well, we're not going to get to this second call to merge sort until we've completely dealt with this left side. All right, so we now have a new call into merge sort. This guy. We ask ourselves, is this sorted? It's not a one list, so the answer is no. So what I'm going to do is I'm going to take the first two pieces of that. We're going to call merge sort on the first half. We'll call merge sort on the second half. And again, the second half has to wait because we're still calling on the first half. So we haven't executed this yet. We also haven't executed this yet. All right, we're waiting on this first half. Is that sorted? No, it's not the one list. So we'll call merge sort on the first half. We'll call merge sort on the second half. Is this guy sorted? Yes, it is. It's a one list, so we don't have to do anything special. We finished that. Then we get to our second call to merge sort. Is that guy sorted? Yes, it's a one list. We don't have to do anything special. So we return from that. So now we're back at this level, and we just returned from our two calls to merge sort that happen to not actually change anything yet. All right, so we're going to have a step now called the merge step. This is where the sorting actually occurs. So the merge step assumes we have two halves of the list. Each half is already sorted in and of itself. So if we look at our picture here, this is my first half, that guy's sorted. This is my second half, this guy's sorted. So the two halves of my list are sorted right now. And what I'm going to do is I'm going to give myself a temporary list that I'm going to merge these two partially sorted lists together into a singly sorted list. So the goal here is to take two lists that are sorted and merge them into one list that is sorted. And the way we accomplish this is we have 2 pointers. Reality is we'll probably create 4 pointers. So we keep track of the begin and end of the, in fact, let's just do that.
Would the list be represented as a linked list, an array, or does it not matter?
Doesn't matter. For right now, you can think of it as like an array. This is an approach to sorting stuff, not necessarily a something related to the type of list.
And is this problem, would you only use it in actual like industry when you have a large data set?
I would say not necessarily. I don't know if that necessarily plays into it. It probably is going to just depend on the type of machinery you're working with. If it has multiple cores, it probably lends itself to larger data with also having multiple cores. That's when it really shines, as being very, very, very fast. Because one thing I want us to notice here as we start doing this merge step, this kind of goes back to Clancy's question. If you remember back to insertion sort, where we had the follower and we kept bubbling the thing towards the front over and over again, you know, that was a little bit complicated when we were doing the sort. And then we had to do the swap, or we had the temporary bucket and things like that. So even though it was simpler to conceive of because it lacked the recursion, the actual sorting aspect of it had, you know, a pretty structured algorithm to it. Whereas you're going to see here that the merge step here is actually pretty simple. We're basically picking teams for kickball here. And you'll kind of see how this works. So I guess to answer your question, though, is it probably lends itself to large data sets. But maybe the better way of answering it is merge sort and quick sort. Let's call these like the two fastest sorts that we work with. They lend themselves to problems where the speed of sorting matters. You know, where most of the problems that we run into are the fastest sort versus the slowest sort is going to be pretty similar in terms of the time that a human being perceives. So we're not really going to notice a major issue. But merge sort would be considered fast. So when speed means something, you might use merge sort. But merge sort certainly would, if you had a computer with a single core on it, which they don't really exist anymore, but let's just say you had a relatively slow computer and a really large data set, even though the merge sort moves are efficient, merge sort would not work well on that machine because you're actually you can't do multiple steps at the same time. So if we think about this right now, I'm just handling this sequentially, but right from the get-go, I made 2 calls to merge sort here. If I had 2 different processors, I could have set this guy to run on processor 1 and this guy to run on processor 2 and have those guys operate completely independent of themselves, only to come together at the end and do that merge step. We're going to handle them as if we only have 1 processor so we can see the individual steps. But that would be an advantage of this on a multi-CPU or a distributed cluster of computers or something like that, like something Google might have where it needs to sort lots and lots and lots of data. Go ahead.
Yeah, so is it kind of like would analogy be that this is kind of like a dev first sort, if you know what that is, where like you're diving kind of into the left, because like right now when it's calling, it's just you're focusing on just the left side.
Let's say yes, there's probably truth to that, but again, I would say that analogy isn't really important. It doesn't really matter whether it's categorized as something like that. This algorithm in general gets categorized as something called the divide and conquer type algorithm. We keep dividing data up until we get to its smallest form factor, then dealing with it in little tiny chunks until we put it back together.
Okay.
So let's kind of look at this merge step here. So one thing I want us to see is, even though this looks a little surgical where we have all these pointers pointing to stuff, remember we have a first half of our list here and our second half of our list here. And each of those halves are already sorted in and of themselves. All right, so I know that this first list is already in order. And I know that this second list is already in order. And what I've just done is I've created some pointers to keep track of where I am in that list. And this kind of goes back to Noah's question. We probably should assume that we're dealing with arrays initially for this, because right now we're dealing with bucket 0 and 1 of our list, right? But when we get over here to the right side, this is bucket what? 0, 1, 2, 3, and 4. This is bucket 3 and 4 of my array. So keeping track of where the begin and end is of the first half and the second half is pretty important, because we're only focused on a certain portion of the array. All right, so at this point in time, the first half of the list begins here and it also ends there. The second half of the list begins here and also ends there. So we're going to ask ourselves, who's the winner? between begin 1 and begin 2. Who's the smaller number between 4 and 1? 1's the winner, right? So we pick 1 as the winner. We place it right there. And because this guy won, we increment the thing that pointed to him. Then we ask the question again. Who's the winner? Begin 1 or an illegal position? Begin 2 no longer points on his list because he's passed up his own end. So 4 beats a no-show. So there's our sort. And then we just copy this temporary array back over. So we overwrite this one and that guy. Now keep in mind that we're operating with that same array in memory. All right, so we passed around the same array, the same pointer to the single array, and just kept track of where it began and end. So when we just changed these 2 buckets, it changed throughout these calls because it's been modified in memory. Okay, so this guy just finished. Let's just leave it like that. So that's the end of this call to merge sort. We have hit rock bottom where we had 2 1 lists, then they bounced back up and we performed a merge. So we have now sorted these 2 partially sorted lists. So that call ends, then we make our second call to merge sort. Is this guy a 1 list? He is. So that we don't do anything. There's no special merging to do for a 1 list. So that ends. So now we have this list that starts at begin 1, end 1, begin 2, end 2. And my temporary array down here is going to need 1 extra bucket because it needs to be the same length as the guy above. All right, so now we do that same merge step again. Who wins between 1, begin 1, and 7, begin 2? The 1 wins. We increment begin 1. Who wins? Begin 1 or begin 2? 4 or 7? The 4 wins. We increment begin 1. Who wins? An illegal position, because begin 1 has passed end 1, or begin 2? Begin 2 wins. So we would copy those values back over, even though in this case, a human being can see we actually didn't make any changes. We still would take our merged list, copy it back over between begin 1 and end 2 in our array. So we have our 1, 4, and 7. That changes throughout. Okay, so now this call to merge sort is done, which means that this first left half guy is now partially sorted. Now we get to our second call to merge sort. This 2 and 3. Is this the 1 list? It's not. So we're going to call merge sort on the first half. We'll call merge sort on the second half. There's our 2 calls to merge sort. Is this guy the 1 list? He is. So we have nothing special to do. No merging, he's already sorted. Is this guy the 1 list? He is. He's already no merging, he's already sorted. So now we have to merge these 2 guys together. So we have begin 1, end 1, begin 2, end 2, and we only need a 2 bucket temporary array for this one. So who wins, begin 1 or begin 2? 2 is smaller than 3. So we do that, begin 1 gets incremented. Who wins? An illegal position because begin 1 has bypassed end 1. This is the beginning and ending of the first half of our list. So illegal position or a 3? The 3? We know we're done when both begin 1 and begin 2 have passed their respective ends. Okay, so there's our answer. We copy it back over. So the 2 becomes a 2, the 3 becomes a 3. Again, we didn't actually make any changes over there. No problem. It worked out to our advantage, but we still have to have the generic logic to do it. All right, so now we have 2 partially sorted lists. And I'm going to need a 5-bucket temporary array to hold the winning lottery numbers from this guy. So now we're going to merge this first half that's sorted in and of itself to the second half that's sorted in and of itself. So who wins, a 1 or a 2? The 1. Increment begin 1. Who wins, a 4 or a 2? The 2 wins. Increment this guy. Who wins, a 4 or a 3? 3. Increment this guy. Who wins, a 4 or an illegal position? 4. Increment this guy. Who wins, a 7 or an illegal position? A 7. All right, copy those values back over. So we have 1, 2, 3, 4, 7, and that made the change in the original array. And we now see we have our list sorted. So that's how merge sort works. The merge step itself, the part that actually does the sorting, is not overly complicated. You know, we're not having to do this whole follower thing and stuff like that. It's going to feel a little bit cryptic at first, but in general, this idea of having kind of 2 kickball teams and then picking the winners from the 2 teams or something like that to create a single list with the best players from best to worst or something like that, I think is fairly understandable. But in order to get to that point, we had to continue to divide our list up and make these merge calls, these merge sort calls, these recursive calls, which are going to be uncomfortable. Okay, so before we go and start implementing some of this, are there questions about this algorithm in general, how it works?
Why wouldn't you just call the merge function after dividing it in half?
Because you're not, if you called the merge function after dividing it in half initially, let me just give myself a screen here. And let's say that I'm going to put these out of order. Here, let's put it definitely out of order. All right, so you're asking, why wouldn't I call the merge function when I have something like this? Right?
Yeah, I think I get it now.
Yeah, that merge function doesn't work.
Yeah.
If you have something like that, because now you're going to ask the question. We just kind of go through it here real quick. We'll see pretty quick what the deal is. All right, we know that our smallest number is a 1 in there, just a human being looking at it. But if we perform merge without having the confidence that the left and the right side are both sorted into themselves, we're asking who wins, a 5 or a 7? And we'll put the 5 here. We know that 5 is not the smallest number out of this collection, but as far as this guy is concerned, it is. Who wins, a 2 or a 7? A 2. Who wins, a 1 or a 7? A 1. Who wins, a 7 or an illegal position? A 7. A 4. So in this case, we actually changed nothing because nothing on the right side ended up winning, but certainly we don't have it in order, right? So it hasn't accomplished what it needed to accomplish. So we have to get to that point where we have that confidence of having a left half and a right half that are already in order. And that's why that knowledge of a trivially sorted list, a list with only one thing in it, is important. All right. So questions about, more questions about this guy, how the algorithm works. Okay, so what we're going to do is we're going to write the first part of this today. And then the second part you'll write, but we're going to actually write the recursion part today, where we're going to go through and we're going to see how this list would ultimately get divided up. So I'm going to actually give myself a, here, let me just steal this slide. Let me just jumble these back up. Something like that. Let's get rid of that for a second. All right, so I'm going to go ahead and create an array that has those contents in it. All right, so let's go over here. I'll create a new folder in here called merge sort. Oh, I'm putting it inside of midterm. All right. And we'll go ahead, and we're actually not going to write this in terms of objects. We're just going to write it inside of a single main. So we'll call this guy driver CPP. And we'll go ahead and have our int main. And we're going to create a integer array. I think I can, what are my numbers here? 72143. I think I can do something like this. Let's actually just write a quick function that will print our array. This guy will say for int I is equal to 0, I is less than size, I plus plus. And we'll go ahead and I'm going to need the IO stream. We'll do cout. We should be able to say AR at bucket I here. our return 0. All right, so let's go test this real quick and make sure my initial assumptions are so there's my initial array. All right, so I created an array, hard-coded it with the stuff that we had in there. Now we're going to go ahead and write merge sort. And what we're going to do initially is we're going to divide up our lists over and over again, showing the portion of the list that we're about to work with. So I'm actually going to say here, instead of print array dealing with a size, I'm going to have print array take in a begin to an end. And we can say the end is inclusive if we want. So we'll say I starts off at begin. I goes all the way up to and including end. I plus plus. So then when we print this guy out, we're going to print out from our array 0 to 4. Show me the portion of the array that we might be interested in. All right, this is going to be a helpful little test thing for us that will allow us to, after we call merge sort, to show us the part of the array we're currently preparing to sort. Okay, so we'll just test this. We should get the same output as we had before because I'm telling it to show me the entire array from bucket 0 to bucket 4, including bucket 4. All right, so we have the same array there. All right, now we want to think about our merge sort on this guy. So since we're not going to actually do the merge step yet, if this is my list, we look at it and we say, is this the one list? It's not. How would we know it's the one list? Begin and end would be the same. All right, so since it's not the one list, we want to divide this guy in half. And I'll go ahead and give ourselves indexes here so we can visualize this a little bit better. This is bucket 0, bucket 1, 2, 3, and 4. All right, so, and I'll give myself our begin and ends again. I know I just took them out. So initially, we're interested in the entire list. When we decide that begin 1 and end 1, or begin and end, are not equal to each other, that means we have something that's not the one list. So let's go back in here. We're going to say void merge sort is going to take in an int pointer AR, an int begin, and an int end. Which portion of my array am I merge sorting? That's what we're doing here. Which portion of the array am I merge sorting? And that's begin to end. So we'll ask the question, if begin is not equal to end, if it is not a one list, it is not trivially sorted, not trivially sorted, then what do we want to do? We want to split it in half and call merge sort on both halves. Now, what I'm going to do here is I'm going to throw a little extra print statement in here. So above here, I'm going to say print array AR begin end. All right, and what I'll do right before that, I'll just do a little cout merge sorting with a little colon, like that. So it'll say merge sorting and then show us the portion of the array we're currently merge sorting. So we can kind of see how the recursive calls are working. Okay, so this isn't even logic. This is just, I just called merge sort on my array starting at this bucket to this bucket. So I'm gonna just print out merge sorting and then show the portion of the array that I'm getting ready to sort. Then I'll ask the question. If it's not the one list, I need to divide in half and call merge sort on each half. So now we need to figure out, how do you divide this guy in half? So you have an array that looks like this, for example, and we need to divide this guy in half. And actually, to make this easier to get right the first time, because it's going to seem easy initially, but I'm actually going to start with a portion of our list here. That does not start off at index 0. Because when we had it starting off at index 0, it would have been, you would have come up with the midpoint in a weird way, and you would have come up with the begin to in a weird way, because we started at 0. By picking something later in the list, but still a half that we know we're going to have to divide, it'll give us a more correct, initially a more correct generic version of begin 1, end 1, begin 2, end 2. All right, you'll see what I mean here in a second. So if, for instance, we're looking at this list, this portion of the list where begin is 2 and end is 4, and we decided that is not the one list, I need now to calculate begin 1, end 1, begin 2, end 2. So now begin 1 will be the same as begin. End 2 will be the same as end. All right, so the beginning of the first half, that's our first half. We know that's our goal. Or possibly that's our first half, and this is our second half, depending on what math we come up with for who gets the larger side. Okay, but we know that the beginning of the first half will be the same as begin, and we know that the ending of the second half will be the same as end. So we can start with that. So begin 1 is equal to begin. End 2 is equal to end. All right, we know those are initial truths. So now we need to figure out, how do I get to the midpoint? Okay, so the midpoint is 4 plus 2 divided by 2. Okay, as opposed to 4, just to show you where you may have gotten tricked before. 4 minus 0 divided by 2 would have given us 2, or 4 divided by 2, the end value divided by 2 gave us 2, and then we would have been tricked into thinking that was correct, when it's only correct when you are looking at the entire list, or you're looking at stuff in the first half. When you get to the second half, that logic breaks down. So the way we calculate this bucket right here is by taking end plus begin and dividing it by 2. And that'll give us our 3. So we're going to call this the end 1. This is the bucket that is end 1. End 1 is equal to end plus begin, or you can say begin plus end, divided by 2. That will give you end 1. Begin 2 is equal to end 1 plus 1. So now we have begin 1 will be 2, end 1 will be 3, begin 2 will be 4, end 2 is 4. So now we have the first half and the second half. That makes sense? So now that I have the information about where the first half begins and ends, and where the second half begins and ends, I can now call merge sort on the first half, passing it my same array, passing it begin 1, end 1, and call merge sort on the same array, passing it begin 2, end 2. So here's my 2 calls to merge sort. So this guy is call merge sort on the first half, call merge sort on the second half. I'll put a little comment here. This will not fire until the entire first half is dealt with. Okay, because when I call merge sort here, this blocks, so I don't get to this next line yet. And this merge sort is going to likely result in 2 more merge sort calls, which will likely result in 2 more merge sort calls, and so on and so forth, until we finally hit something that is the one list. We're only doing this stuff if it's not the one list. When we finally hit a one list, what do? We do nothing. So we can even put a little else here. Say cout one list, do nothing. That's what we do in the else. And then what we'll do here is we'll put a little comment. Now perform the merge step.
Can you explain what's going on with begin 2 again? Because it seems like adding 1 is adding like a hard-coded value to begin 2. Not sure what's going on there.
Yep. So if end 1 is the end of the first half of the list, then the beginning of the second half of the list would be 1 past that.
So it's moving buckets rather than values.
Right, so it's based off of N1. So N1 is bucket 3 in this case.
Okay.
This was the middle, and we decided that the middle becomes part of the first half. We just decided that was the case, that the first half will be our larger half. And because of that, if that's where the first half ends, then the second half would begin 1 bucket forwards from that. That's why we're hard coding a 1 in here, but we're hard coding it based off of whatever end 1 is. So end 1 was calculated, and then we're just saying begin 2 starts 1 bucket later. Does that make sense?
Yeah, that helps.
Okay, so what we're going to do here, I'm just giving you some hint code here for your homework. So now we have to merge. Start to cry, Clancy.
Why just me? Why do you have to do that?
Hey, you made the comments. That's a star for the day. All right. So, all right. So this guy is now going to go through when I call merge sort on the original list. So this is going to be merge sort, passing it my array, telling it I'm starting at bucket 0, going to bucket 4, because that is the range of my original call to merge sort. I want to merge sort my entire array. This guy's then going to say I'm merge sorting. He's going to show me the entire array. Then he's going to figure out begin and end, and he's going to call merge sort in the first half and then the second half, but we're going to see him deal with the entire first half first. All right, so let's go ahead and just see this guy run. All right, so we're merge sorting 7, 2, 1, 4, 3. Then we see we call merge sort on the first half, 7, 2, 1. Then we see we call merge sort on the first half of that, 7, 2. Then we see we call merge sort on the first half of that, 7. We notice that's a 1 list, do nothing. Then we call merge sort on the right half of this guy, the 2. Then we notice it's a 1 list, we do nothing. Now we have to merge. We're going to merge the 7 and the 2 together. I haven't written that code yet. That's your homework. All right. And then we get to, oh yeah, here's the start crying Clancy. Don't forget about that part. Probably need to put a little /n in there, but that's okay. So now we're merge sorting the second half of this list. We notice it's a 1 list, have to merge. So now we're back up to that. Then, where are we at here? We're finally hitting this is our original call to the second half. We're finally getting to merge sort on 4, 3 after we've completely dealt with the left half. So here's merge sort on 4, 3. Merge sort in the first half, it's a 1 list. Merge sort in the second half, it's a 1 list. Then we have to do the merge for the 4, 3. So now we have to merge. Once we get to that, we're done with we're back to our final call, 7, 2, 1, 4, 3. We've printed out all the things that we are going to do. So now this guy is sorted in and of itself, assuming you wrote your merge right. This guy is sorted in and of himself, assuming you wrote your merge right. Now you need to do a final merge to get these two guys, or get those two halves merged together to give you your final list. All right, so when all is said and done, if I come back in here, if this worked, I should be able to do print array AR 0 to 4, and he should show me a sorted array. Right now he won't because we haven't done any merging, but in the end, he should show me a sorted array. Let me go ahead and put the start crying Clancy thing with the /n. I got kind of giddy on that one. But we'll leave it in the comments just because.
Understandable.
Yeah. So this, in the very end, should be our array sorted. But since we haven't written any merging here, it's not sorted. Okay? So your homework for Tuesday is to implement all of these places where it says, now we have to merge, start to cry Clancy. That's that merge step where we pick who's the winner, begin 1 or begin 2, put it into a temporary array, calculate that, and then copy it back over to the correct place that we're currently focused on in the array. All right, questions about any of that? And what I'll do is I'll just paste this code into Slack because we only have one file here. All right, questions, comments, concerns, bribes.
Wait, shouldn't it be now we have to, you have it as no, we have to sort. We have to merge.
Yep, that's gonna
now.
I say now we perform the merge step.
Yeah, like,
oh, so well you did Clancy's job is what you're saying.
yeah, basically. That's why I put it in the chat.
Okay, good. All right, so I'll hang around for a little bit in case there's any questions. I know a couple people said they wanted to meet with me afterwards, but so I'm not going anywhere. But we're done. I will see everybody on Tuesday. Stay safe, stay healthy, all that jazz. And I'll probably just end up restarting Zoom later to figure out why my images are going away. It's weird. I will stop the recording.